In this video, I want to provide an introduction to maximum likelihood estimation by means of an example. So the example I'm going to be talking about here is the example of the UK population. So the idea is that there are something like 70 million individuals in the population. And of course, we don't have the entirety of the data on them. We only have a sample from that particular population. And from the sample, we have, I don't know, maybe n individuals. Okay, so let's say we were interested in evaluating what the probability is that an individual was male, given that we only have a sample from the population. How might we go about thinking about this? Well, the idea is that we could suppose that there is some sort of distribution function or probability distribution function which basically determine the probability that a given individual is either going to be male or female. Okay, well the idea is that we can actually define a function like this, our probability density function, which we're going to call f, and we're going to call it f of xi given the probability p. And I should stress that p is a population quantity and in general is the thing which we're trying to estimate, but I'm just going to assume that we know p here to start with. So xi here is going to be a dummy variable which is going to take on the value of 1 if an individual is male, and it's going to take on a value of 0 if the individual was female. And f here is actually going to be given by p, where p is the probability that an individual is male, to the power xi times 1 minus p to the 1 minus xi. Okay, so this looks quite complicated. Let's talk through how it actually works. So the idea is that if an individual in our sample is male, then what value does f take on then? So this is a function of 1 now, given that we have the probability p. Well, if we just substitute in 1 for xi here, we're going to have p to the power 1 times 1 minus p to the 1 minus xi. Well, xi is just 1, so that's going to be 0 here. And anything to the power 0 is just 1, so we're just going to be left with p. So our function here, f, tells us if that individual was male, what is the probability that we would have got that observation? And that's just going to be given by p, the probability that an individual is male. Similarly, if we are thinking about an individual being female, so this is a function of 0 given p, and this would just be given by p to the power 0 times 1 minus p to the 1 minus 0, so it's just going to be 1 minus p to the power 1. Well, p to the 0 is just 1, so it's just going to be 1 times 1 minus p. So our function f evaluates to 1 minus p, which is actually the probability that an individual is female. So in both circumstances, you can see that our function f is telling us the probability that we would have got that observation if indeed it was the case that we can sort of think about our observations as being almost like tosses of a coin. Okay, so that's the circumstance for one observation. How about if we have a sample of n observations? So in that circumstance, what we'd quite like to define is we'd like to define a probability density function f for the n individuals. So this would be f of x1, x2 through to xn, given that we know the probability p of an individual being male. Well, that's not hard to calculate in the circumstance where we're considering observations being a random sample. In other words, they are independent of one another. It's just going to be the individual density functions multiplied together. So that's just going to be the probability of x1, or p to the power x1, times 1 minus p to the power 1 minus x1, times p to the power x2 times 1 minus p to the 1 minus x2. And then we continue on all the way up to p to the xn times 1 minus p to the 1 minus xn. So all we've done is we've multiplied together the individual density functions f of xi given p. And we can actually write this whole thing a little bit more neatly by writing it as a product. And so we're going to use the product notation. This capital Pi here means that we're going to calculate the product of all the terms, and it's going to be the product from I equals 1 to n of p of xi times 1 minus p to the 1 minus xi. And this product term here, all it means is it means that we're going to multiply together all of the terms which are specified by xi. It's kind of like the equivalent of the summation notation, but when we're talking about products. And when we sort of multiply together each of these individual density functions, what we're actually going to obtain is, in the discrete case, we're going to be talking about what was the probability that the random variable x1 actually took on that value of x1. So what was the probability that the random variable x, which determines the sex of an individual, actually was, let's say, male for that first individual we actually pulled out and was male. And we're also talking about what was the probability that the random variable x2 also was, let's say, its particular value of x2 which we obtained in our sample. And we're talking about the joint probability of all these things occurring up until we're talking about what's the probability that the random variable xn actually took on that particular value of xn. So it's kind of like the joint probability that we would have got this sample of observations from our population. And this joint probability is what we define as the likelihood. So the likelihood in a discrete case is the probability that we would have got all of these observations given that there was a probability p of an individual being male. In general, we don't know the parameter p, and indeed it's probably the thing we're trying to estimate. So how does one do this from a likelihood perspective? Well, the idea is that what we want to do is we want to maximize the probability that we would have got this sample of observations over choice of p. So what we're actually going to do is we're going to differentiate this likelihood function with respect to p and set it equal to 0. So the idea is that we're trying to maximize the likelihood, or rather we're choosing the probability to maximize the likelihood that we would have obtained that set of observations, given that the individual xi has a probability distribution which is specified by this above f. So that's the idea with likelihood. We're trying to maximize essentially some sort of probability or joint probability of getting that sample of observations. The problem with differentiating this function down here as it stands is that because it's a product, that's actually quite a complicated thing to do. We have to essentially use the chain rule, or the product rule rather. And because we've got n things in our product, it's actually going to be a really, really complicated thing to differentiate. So as it stands, it looks like it's sort of all might be lost, but in fact it's not. And we're going to talk about potential solutions to this problem in the next few videos, and how we can actually derive the maximum likelihood estimator of p, in this case the probability that an individual is male.